Alright, ogives are very, very similar to histograms. And you basically take a histogram and you add up your tallies as you go to create your ogive. So a couple things to note about ogives. These are percentiles. As long as this is turned into a relative cumulative frequency, or if you have a percentage going on here, these are percentiles. So like this point right here, the 300th percentile, or sorry, at 300, we're at these look like they're going by fives, we're at like the 10th percentile, which means that 10% of the data falls below 300. Over here at 400, it looks like we're at the 45th percentile, which means 45% of the data falls between these, below this. Now, how much falls between 300 and 400? We'll figure that out. If this is the 45th percentile, and this is the 10th percentile, you just subtract the two. You get 45 minus 10 is 35. Now, if you're going to do that, show me 45 minus 10 equals 35. Because if you think this is 5 instead of 10, and this is 40, so you've got 40 minus 5 is still 35. Well, that was stupid. Let's say you think this is 15. So if you say this is 15, now all of a sudden you got a totally different prospect. We're talking about 25 here in between these two. So if your answer is just 25 and my answer is 35, without any work showing, it's really kind of hard to tell if you're doing this the right way. Which for the most part is just eyeballing this graph. Other things to say about them. Works both ways. You want the 75th percentile, you start at 75, move this over, and that would be 500. When you're creating your own ogive, your right endpoint is your percentile. The left endpoint starts at your last place. So you're starting at 0, and you end at 100 always. When you guys are making your own ones, a lot of people forgot to connect to 0. Alright, so now we're jumping down to box plots. And a box plot basically is off of the 5-number summary. And the 5-number summary, in recap, is your minimum, is your Q1, is your median, is your Q3, and then it's your max. And big thing here is a lot of people pick this maximum on the quiz to be, well, let's say we had a box plot that looks something like this. First things first, I would say this box plot is skewed to the right. Oh, and we're going to put an outlier out here. And when we're looking at the numbers, I can see my 5-number summary right here. So this would be my five numbers. So let's say this is 1, this is 2, 3, 5, 7, and then 8. So my 5-number summary would be 1, 2, 3, 5, and 8. 7 is not going to be the maximum. 7 is the highest non-outlier. It might be the fence, and it might not be the fence. So the fence would be basically based on your outlier rule. So you find your IQR. So that's 5 minus 2 is 3. So the IQR is Q3 minus Q1. So in this case, it would be 3. And then what we have to do for the outlier is we take 1.5 times the IQR, which in our case would be 4.5. And we add 4.5 to the right endpoint, and we subtract 4.5 to the left endpoint. So we get a problem here, because if I add 4.5 to 5, I'll get 9.5, which 8 would not be an outlier then, right? So we got to change 8. 8's no good for my example. I have to make this something like 12. And then my scale is all messed up. Like if it's supposed to be 2, it's got to be way out over here somewhere. But that's still okay. So the question some people have is, why in the world doesn't this go up to 9.5? So if 5 is here, if I add 4.5 to it, I get to 9.5. That's the upper limit of, that's the fence, if you may, for outliers. However, in my data set, I don't have a 9.5, so I can't put it there. The next highest point I have is 7. Now, if you look on the other side, if I subtract 2 minus 4.5, I get a negative 2.5, which is way down here somewhere. But the lowest non-outlier that I have is just 1. I might have a whole lot of points in here, and I might have a whole lot of points in here, but they're all between 1 and 2. Another misconception I saw, people think that this box is bigger than this box because there's more values in there. It's not true at all. All it means is that of these quarter of the values, 5 is 2 to the right, then 2 is only 1 to the left. It doesn't even mean that they're more spread out. It just means that the highest one in that quartile is farther than the lowest one in this quartile is. So it's kind of, it can be misleading. So I can have almost all these values right in here and just 1 over here. And I can have all these values in here and none over here. And I still get the same box plot, which might even cause me to have trouble even skewing this, even though that's what it looks like. However, there's still points out there, especially with the outlier, that definitely pulls my mean way out to the right. Frequently, one of the words that we've seen in this chapter, it's resistant. It's an I in the middle there. So, if something is resistant to an outlier, basically if it has resistance, that means it's not really affected by the outlier. So things that are resistant, the median. If I take this point and bring it farther out to the right, it's not going to affect my median because the 12th gets knocked off with 1 and the median is the same. The mean is not, because the mean is definitely pulled by far out values. Oh, the IQR. Almost everything with the box plot is not going to be affected by outliers. This, if I move this 12 farther out right, it really doesn't affect anything in my box plot, if you notice. It'll affect the outlier part, but it doesn't pull this. It doesn't pull any of the whiskers. It doesn't pull any of my quartiles. If I add more points on the right, it will affect my box plot. But box plots in general, besides their outlier, is resistant to outliers. I mean, outlier itself isn't, but everything else is. So when you're looking at data with outliers, box plot sometimes is a better way of looking at it because of the fact that you might end up throwing out the outlier. And if that's true, then the box plot's not going to be all that changed by it. Things that are not resistant. We talked about the mean. The standard deviation and variance are definitely not. They are very affected by outliers. So if you don't want those outliers to have a huge effect on things, then we really want to be talking about the median and the IQR. If we want to see the effects of those outliers, then you want to talk about the mean and the standard deviation. So bringing back the Bill Gates thing, if we really want to know what's the average amount of money that we have in the room, we would want to know about the median and the IQR, because that would be representative of our group. If we did want to have them come into effect, then we talk about the mean and the standard deviation. But the standard deviation would really mean not much at all. So you have that one outlier way out there that's throwing everything off. It really depends on your data which one set you want to use. But you need a center and you need a spread, right? So center and a spread, you have to choose between them. And each problem kind of presents which one it wants to. And hopefully on the AP exam, it just tells you what they want you to talk about. Alright, so standard deviation and variance. Jump down right at the bottom of page 27. So standard deviation, and these should really have S of X on them. And I gotta fix that. Maybe I'll do that while I'm in this computer before I turn it off. But we'll see. So standard deviation is basically the average distance from the mean. That's what the standard deviation means. And therefore, even when you're talking about units, it's a distance from the mean, and the mean is in units. It's like inches, it's feet, it's pounds. So when you're talking about standard deviation and you want to talk about it in context, you go back to the context of the problem itself, look for the question, and try to answer it in that vein. Now, it is a measure of spread, and variance is also a measure of spread. If you're talking about the units on variance, though, if you're talking about inches, it'll be inches squared, because everything is squared. It really doesn't matter when you're talking about spread which one you talk about. You can use either one, and it will still suffice for the problem. These equations are in the orange packets if you need them, but for the most part, you're going to use your calculator to do your standard deviation and your variance. You can run one variable stats. If you want the variance, you can either go second stat, go over to math, and do variance of list 1, or find the standard deviation. And the calculator looks like this. You don't want to use this one because this is for the population. It'd be great if you had it, but usually we don't. Alright, now that brings us to linear transformations. And linear transformations are, I think, very, very obvious and very useful and kind of quick, and I actually like them a lot. So, when you do a linear transformation, anything in the form a plus bx is a linear transformation. There's no squareds, there's no powers of any sort. This is a linear equation. You can add in the linear equations, you can multiply. Now you can also subtract and divide, because b could be 1/3, a could be a -5. And it's the same thing as the mx plus b, but it's kind of rearranged in a different looking format. Now, you have your data, and you can find your mean, you can find all this fun stuff. Use your one variable stats. You could add 4 to your data set and run one variable stats and everything. But once you have them, you can just use the rules. Actually, I'm going to bust this up and look at the rules just above here on the next page, because I don't want to do it with the actual numbers. We'll just talk about it in general. So, recapping, when you have them, either the mean or the median, and you want to run an a plus bx transformation. So our x new is a plus b times the old x. Now, when you're having any measure of center, whether it's the median, which is just above this, or the mean, you really just take your a plus b and then take your mean of the old, multiply it by b, and add the a. You have to do both for any measure of center. They get shifted over and they also get stretched. However, ranges only get stretched. It's going to be b times the range. If you're doing the IQR, that's a measure of spread, so it gets stretched. It gets stretched by b times the range. Nope, the IQR. I did that in class as well. Talking about standard deviation, it also is a measure of spread, so it is a stretch. It's b times the IQR. No, it's b times s sub x. Alright, and now the tricky one, the variance. So it's basically b squared times the variance. But that's a little bit trickier to understand. So the way to understand it is b times the standard deviation. Well, how do you find variance if you got standard deviation? Well, you square it. So it's b s sub x squared. So what is that? That's b squared, and then s sub x squared, which is your variance. So if I use this notation, it might clear things up. So slightly. So that right there is probably the trickiest part to the end of this chapter. So what's in the chapter? We got making graphs and understanding graphs. We have talking about what is a distribution. We've got standard deviation and variance, and we've also got these transformations. Remember, every time that you write something, make sure you write your answer in context. I will take off points for that on the test. When you make a graph, make sure you label your axes. If you have a y-axis, it's probably frequency or relative frequency, but you need to have one. If you're making a dot plot, you don't really need a y-axis. If you do, it's a frequency, but then you have to make sure that all your dots are exactly the same height, and they really should be. But a lot of times your tick marks are going to be really, really hard to go across, so usually you just make dots on the graph. What else to talk about? I don't know. Look through your FRQ packet. Any one of those problems is fair game on the test, and that's due test day. So good luck and have fun.